So let me just say it's really wonderful to be here and to see what a flourishing field this has become. The first NeurIPS meeting was held in 1978 in Denver. And, you know, neural networks are really becoming very, very interesting as an alternative to symbol processing, rule-based logical AI. But what we didn't know was how long it was going to take. Now, what happened with NeurIPS is that the field morphed into the premier machine learning conference. And then in November 2022, I went to bed as the president of the foundation that organizes, the president of the foundation that organizes NeurIPS, and I woke up as the president of the foundation that organizes the premier AI meeting. This was an overnight success that took 40 years to create. But in fact, it's neural networks all the way down, right? It hasn't changed since 1978 in the sense that it's built up, and now computation has caught up, and we now have seen what happens if you can get scale. Okay, so here is, okay, so I went to a meeting which was organized by the National Academy of Sciences, 2017, was organized by mathematicians who were very interested in deep learning. And I gave the final summation. And here's what I told them. I said, look, these neural networks, deep learning networks, are just mathematical functions. And who knows how to analyze mathematical functions better than mathematicians? And really, what was interesting was that the message here, and this was the PNAS paper that followed, was that we were exploring the mathematics of high dimensional spaces, and it's completely different from your intuition based on low dimensional spaces. In every area of mathematics and statistics, optimization theory, it's all got to be rewritten. All the textbooks have to be rewritten, and even control theory, per se. That's going to change too. When you're in a very high dimensional distributed control system, that the brain is actually doesn't have a centralized controller, it has a distributed controller. So this is where we're headed. Mathematics is going to save us. And we all know here what happened. AI vastly underestimated the amount of computation that is needed to solve these very difficult problems. And at the beginning, you wrote programs, try to be intelligent by writing an intelligent program. But the cost of programming went up, the cost of computing goes down. And that crossed around 2012 when Jeff Hinton and his students reduced the error in ImageNet with convolutional neural networks by 20%, which is about a 20-year jump into the future for computer vision. And GPUs were mentioned. So this is how much computing goes into creating a particular network, measured in petaflop days, right? And you can see neural networks starting in the 1980s. NetTalk, that was mine. Okay, you see it's at the very bottom here. We use the VAX. And there's Moore's Law. It says it's doubling every 24 months, but I think it's more like 18 months. But there's an inflection there because when GPUs started being used, it's not just that it had more computing power, the doubling time was reduced to 3.4 months. And that's where we're at now. It's no longer Moore's Law, it's someone else's law, GPU law. Now, it's not just computing, it's also data, right? That was also important. And very data poor back in the 80s, but then now we were in a data rich era. Now, one of the things that is really important in a lot of applications is temporal context. And somebody mentioned that, everybody thinks that the space is the final frontier. How many know the origin of that? Star Trek. Time is the final frontier. And as Carver once said, time is its own representation. And temporal context can be seen in almost every application. For example, text, that's very familiar. We have these very long inputs now to these GPTs. And the goal is to try to be able to link words that are far apart in sentences and paragraphs across a very large part of groups of paragraphs. That's true for audio, it's true for video. And so how do you do that? Well, recurrent neural networks are very popular for language translation. And the way they did it was by recirculating the information. The words come in one at a time, they get embedded. This is time going from left to right, and this is the same network now unrolled in time. And you can see that once you get to a certain point, you get the go signal, the words are coming in English and they come out in another language. And it's all trained with backprop through time. And it worked. It actually did a pretty good job, but it had a problem. And the flying ointment was that if you had a lot of words coming in, that the trace of the first word would die down. And so by the time you get to the end, you couldn't connect it to the last word. But that was fixed with Band-Aid with long short-term memory. And the way they did it, as you can see there's in the middle. By the way, is there a pointer, laser pointer? Be easier for me to point to things, but that's okay. No, don't worry.
There could be your pointer there. He can point for you.
I don't want to. I want to touch it. Okay, look, I can just point. Okay, you see that little circle in the middle with a recurrent. Well, that turns out to be a unit that basically something inside itself, so it will remember. It's like a working memory over a very long time. Thank you. Over a very long time. There, that's the one. And there's a gate, and that goes in and comes out, and all of that is learned. But the point is that it's having, it gives you a little bit of internal memory that will remember the first word. That helped, but it's still not as good as what a transformer does. So this is the diagram for how information gets into the transformer through the inputs that you give it, and also the output is going to come out as you see it goes in, and then there's a feed-forward network. The output comes out one word at a time. It's a generative network, and that word comes back to the beginning, and it circulates over and over. You get one word after the next. Now, how did the transformer get around this decay problem? It did it with long input vectors. That now, it was like 10,000 and then 100,000, it's now to 1 million. In other words, they can keep track of 1 million words. You can give it a whole book, and it'll keep track of what happened in the first word of the book and the last word. I mean, this is really amazing that this has been done. The secret sauce is the multi-headed attention. And the way that works is to create a matrix in which the entries of the matrix tell you for each pair of words what the relationship is between them, how good is the association, and this will help with things like clauses and things across sentences, like prepositions and so forth, this, then, and so forth. So here is one of the boxes just to show that here's the embedding going in. Here's the attention head, multi-headed attention, self-attention. And you'll see that what happens is it's actually a parallel pathway. You get the input going directly in, and that's joined by the head, which helps you understand the relationship between words, not just the fact that they are in a particular order. And then there's a feed-forward network, and that's repeated. This is just one little box, which is stacked up many, many deep. Self-attention is the secret sauce. Now, very recently, the problem with self-attention is the matrix, and it increases with n squared. That's very bad scaling, right? You want something that's order n. And actually, that was recently achieved by replacing self-attention with linear state space models. Now, this is all familiar stuff to engineers. If you're in signal processing or control theory, this is bread and butter. You have the input coming in, You have an internal state X, which is a differential, first order differential linear equation with matrix A, and then there's an output Y, right? And so there's an input matrix B, there's an output matrix C, and then there's this internal model X. So let's apply that and replace the self-attention with one of these state space models, but it's not going to be just any, it's going to have a special structure. It's called a tuplets matrix. So A is going to be diagonal, the same value along the main diagonal, the same value, a different value along all these diagonals, as you can see here. So it has order n parameters, which is good. Now, the tuplets matrix has a lot of other properties too. This is a huge literature on this. It turns out that what it's doing is the equivalent of temporal convolution. And it could be used for things like Fourier transforms and all sorts of other things, right? So it's a very powerful kernel. So there was a group, Albert Gu, who was at the time a graduate student at Christopher Reeves Lab at Stanford, replaced the self-attention with a tuplets matrix they call HIPPO. And the details aren't important, except to see here, HIPPO, as you can see, this is a particular CFAR 10. It's a very small data set of images. But the idea, though, is that HIPPO learns faster and achieves a higher performance than the other types of matrices, for example, random matrices in red. And you can either freeze the matrix or you can train the matrix starting from the triplets. Now that was improved by Albert Gu. He moved to Carnegie Mellon, and so here's a state space state space model, and he calls it Mamba, and it's a different triplets matrix, but he showed that he could achieve performance which was as good or better than the self-attention model on a whole range of problems. So for example, here's first of all the models that Mamba was being compared to, different sizes, 130, 370 million, 70, 1.4 billion, and so forth. And then here now are all of the tests, the tasks that need to be done. And you can see in almost every case, Mamba does better than the traditional transformer systems, just looking at the goals, right? So this is amazing because it's order n. It means it's much more efficient to train and much more efficient at inference. Inference time is 60 times faster, 60. And if you think about that, that's like 2 orders of magnitude, and that of course is where all of the cost comes when you're using it. When you have hundreds of millions of users hitting it in the cloud, picking up 2 orders of magnitude is a real big win. So this is amazing because the brain is a very complex dynamical system, and it's been modeled by state space models, not nonlinear models, but nonetheless. Dynamical systems can replace, like putting a recurrent network into but the beauty is that with these tuplets matrices, you can actually come up with an analytic solution. So you don't have to go through the recurrence. You can just play it out because you have the solution, analytic solution. Now, let's jump into the brain, okay? So if you look at the connectivity matrix in the cortex, it looks like this. Here's a neuron that is getting excitatory inputs. This is the strength of the weight from neighboring neurons in the column. And then from more distant columns, it's getting inhibitory inputs, right? Positive nearby, and this is the Mexican hat. This is the classic connectivity pattern. It's been known in neuroscience for decades, going back, to the early days. Anatomists told us that. So here's what this connectivity looks like in the form of input-output relationship, presynaptic input, and this is a postsynaptic neuron. And so here's the Mexican hat, here's the cross-section. If you look at this matrix, it's a tuplets matrix. The cortex nature has discovered tuplets, the beauty of tuplets. And what does it do computationally? It turns out that you can create a line attractor with this connectivity matrix. A line attractor, unlike the Hopfield point attractor, line attractor has neutral stability. And therefore, when you go downhill to the bottom of the valley, you can be pushed along very, very easily back and forth. And this is called and if you connect it up a one-dimensional ring, this is called a ring network. Again, it has a long tradition in neuroscience. And this is a model that was developed by Lyle Muller in my lab. And it has the connectivity you just saw, but in addition, it puts in time delay. It turns out neurons not just are connected with each other, but there's a time delay between the input and then the axon has a time delay, and therefore the further you are away, the longer the delay. So you put that into the model. And here is what you see when you get the thing working dynamically. So what you're seeing is the average activity of units along the ring, and you can see it's a traveling wave. It's a traveling wave. This is information that's flowing around the circle in both directions, by the way. It's symmetric. And you can see sometimes it gets coherent, and sometimes the waves rise, and sometimes they fall. And if you do a Fourier analysis, spatial temporal, you can see this characteristic slope, which is the velocity of the wave. Power spectrum looks just like the brain. Falling off is 1/f². Okay, so let's put this Toeplitz matrix, this traveling wave, into a recurrent network and see what it can do. So if you use, this is work that was done in collaboration with Max Welling and his then graduate student, Andy Keller. And first of all, people who do recurrent networks in AI, what they do is they start with random connectivity and then they learn it, right? And you don't get any traveling waves if you do that. But if you start out with this Mexican hat, you get beautiful traveling waves. This is time going down. Here's activity. You can see it travels with a constant velocity. This is, we call it convolutional recurrent neural network for temporal convolution. So what can you do with it? Let's ask it to do a simple copy test. This is one of the simplest tasks that you can ask a recurrent network to do. What you do is you give it a binary input pattern, as you can see here. Then you give it a go here, and then the output should just reproduce the input. Very simple. This is not a big deal. Just have to memorize a few bits. But you can introduce a time delay of 10, 30, 100, or more. And what we're going to compare is the wave neural network or convolutional neural network with the traditional one, that it doesn't have any particular format or form. Well, first of all, you see it has no trouble with reproducing it, whereas the traditional recurrent neural network learned with backdrop is struggling even just to reproduce the pattern. But look, after a delay of 10, perfect. After a delay of 30, perfect. Whereas it just wipes out. There's just no information available after 30 steps, right? Now, what this means that traveling waves allow you to propagate information into the future very actively, right? Okay, now, is it accurate? But the training, the time is much faster. So, for example, here's the training in red of the wave neural network. And this is a log scale, mean square error, 10 to the -3, 10 to the -5, 10 to the -7 in 100 epochs, right? And you can see it's struggling. Backdrop through time is struggling here with this recurrent network. And look at the learning is even faster for t equals 30 and t equals 80. And it's gone up to several hundred steps. This is phenomenally fast learning. This is not the kind of learning that is used right now in transformers, which has to go over the data over and over and over again. And the latest GPT-4 took 2 months with 10,000 GPUs to train for $100 million. And GPT-5 is going to cost $1 billion. I just read. Okay, here's one more task. We did about a dozen of these tasks, but this one is even, I think, more remarkable. So the task is the following: that you give it a sequence of numbers, and then every once in a while you give it a signal to remember this number. And the next time you get the signal, you add it to the old numbers. And, you know, and then at the end, tell me what the sum is, right? So this is, you know, it's random when the time comes that it's supposed to remember the number. And here's the wave neural network. An error here, as you can see, 10 to the minus 6, all the way out to a sequence length of 100, it nails the sum. And as you can see, only after 2,000 iterations, compared to the traditional backdrop through time, which is struggling with at 30,000 iterations, and it fails completely when you get above that. And look at how fast it learns. This is amazing. So it can do arithmetic, right? It can learn how to do arithmetic. The very same network that remembers can also do some sort of processing. And Arjun Karabali, who is a student of Hava Siegelin, has actually shown that you can also do variable binding with this, like, you know, x equals 7. And then remember that, right? So this is really quite remarkable. I think that these waves are really the wave of the future. Now, it turns out that the brain is filled with traveling waves, and neuroscientists have known this for decades. But it's been ignored because they can't fit it into the traditional way that they think about activity patterns in neurons. And I'll get into the details, but first I want to show you the evidence. And there's waves at every scale, spatial scale. So this is my levels diagram starting from the molecular level here, the angstrom level, all the way up to the entire central nervous system. And you have synapses, neurons, networks, maps. And there are traveling waves that are local to specific areas like V1. There are mesoscopic waves that go between areas. And then finally, when you fall asleep, there are global waves that go over the entire cortex and are thought to be important for memory consolidation of experiences you've had during the day. The other thing that happens in a hierarchy, which we know happens in the visual system and the auditory system, even in the motor system, there's a hierarchy of areas, V1, V2, V3. Now, if we're right about the traveling wave having this kind of Mexican hat connectivity, that's going to happen at each one of these levels, which means by the time you get to the top, you're going to be integrating information over long stretches of time. Maybe in V1, it's only over 100 milliseconds. Maybe when you get up to the infratemporal cortex, it could be maybe many seconds, maybe minutes. And then finally, that goes to the prefrontal cortex, which we know can hold on to information for much, much longer, the working memory, planning. And there are traveling waves in all of these areas. Here's an example of a traveling wave in primary visual cortex of the mouse. Mark Snitzer has improved optical recording from voltage-sensitive dyes, looking down at V1, and these are 3 millisecond frames. You can see there's a traveling wave across the cortex at 2 different time points. 2 millimeter is a long distance in the mouse cortex. It's a very small cortex, about a centimeter across, and you can see that there's a time delay between different points along this traveling wave. And this has been known for actually at least 20 years, but now we can actually go down and actually see it by recording from specific points, but now we can actually see the whole thing globally. So here now is recordings from the human cortex. This is work that was done by Lau Muller and recorded from humans who had epilepsy operations implanted with grids of electrodes, 10 by 10, in order to isolate the focus of the seizure. And they would have to wait for a couple of weeks for the seizures to come. And so in the meantime, we're collecting the data and we can analyze it. So here's what we did. During sleep, there are these sleep spindles, and the sleep spindle lasts for 1 or 2 seconds at 10 to 14 hertz, thousands of times during the night. And this occurs in between REM, rapid eye movement sleep, and deep slow wave sleep. So you can't go between them without stopping and doing a little bit of spindling, right? And it was thought for many years, including Mircea Sterian, who I collaborated with for 15 years, he put electrodes in different parts of the cortex and said they're synchronous across the whole cortex. Well, here are the recordings now, which have been filtered in 10 to 14 hertz band from here in red, one location, and then in gray, all the other locations. And you can see, there's a little bit of synchrony here, depending on how far away you are, but there's a lot of noise. In fact, if you don't filter it, there's a lot of noise, and so it's hard to figure out where the peak is. And our method was to analyze not the peak, but the phase. And with that, and using algorithms from fluid dynamics, we're able to actually look at the pattern, the dynamics of the pattern across the cortex. So white is 1, and we normalize it to 1 plus 1 minus 1. So just focus on the white. You can see it's transiting from the temporal cortex to the occipital to the prefrontal cortex. It's a circular traveling wave. And we've since repeated this in babies who sleep a lot and have very thin skulls. It's not yet solidified. And the spindles there are across both hemispheres. And they don't have the additional difficulty of worrying about epilepsy, perhaps having something to do with the measurements that we're doing. So this is happening in your brain when you fall asleep thousands of times. And we know that the number of spindles you have during the night, we can manipulate that. And we know that the more spindles you have, the more you remember from the previous day. So this is a direct measure of something that's going on in the cortex, and we know it's the hippocampus talking to the cortex, playing back experiences during the day. And that gets integrated into the long-term memory in the cortex. Now, the mother of all oscillations have been seen literally, we're talking here about over 30, 40 years, is in the hippocampus. It's the theta oscillation, which is 4 to 8 hertz. Now, let me just give you some background here. So they're called, in the neuroscience literature, they're called oscillations. And unfortunately, that word has a connotation, which is synchronous firing. And it's true, if you measure 2 neurons next to each other, they're probably pretty close to synchronous. But I just showed you examples where, no, they're not synchronous. If you look broader, both in terms of, locally within V1 and then across the whole cortex, they're traveling waves, which means space and time are being integrated together in some kind of a population code. And you're representing not just at a given moment in time, you're representing not just the sensory information coming in at that moment. You're actually in that population encoding what's happened over a window of time. And that's a much more powerful and much more rich representation. And it's not one that it's not easy to imagine. It's not, and there's no reason why nature should make it easy for us to understand, right? We're not used to it. But the problem is that neuroscientists have this view that, okay, V1, retina gives a frame of information to V1, and that's processed, and now that's a representation of what happened in the retina, and then that frame is passed to V2 at that time, and that's all that, when you record from neurons, that's how you interpret the signals. But if this is correct, it means that if you try to reconstruct what the input is, you should be able to reconstruct not just what happened now, what's happening now, but what's happened in the past. And the further you go up in the ladder, in the layers, you should be able to reconstruct further and further into the past. This is a prediction, and that could be tested, but nobody's actually done that yet, but it's interesting. Now, as I said, the theta wave is probably it's the largest oscillation, and people who study the hippocampus are very familiar with it. They use it because when the rat is moving in the environment, you get huge theta. As soon as the rat stops, then it goes away. So it has something to do with exploring, right? Sejnowski at Caltech was one of the first actually to notice that if you put in electrodes, an array of electrodes across the hippocampus of the rat from dorsal to ventral, and here are all the recordings, and then look at the array of the temporal going down now. This is time going to the right, and this is the array down. That it's a traveling wave from dorsal to ventral. And if you don't believe me, oops, here is the recording. If I can get this started. Ah, merge that. Okay, well, you have to imagine this. Okay, imagine a white streak going from the dorsal to the ventral, and it just goes over and over and over. So I have colleagues who study the hippocampus, and I'm on their thesis committees at UCSD. And every time at the end of the defense, I ask them, have you considered what traveling waves in the hippocampus, what implications it has for your results? And here's what they say: that's not my problem. And it's not just the students, it's the faculty who believe that. And this is now so well established that these traveling waves exist. We published, Lila and I published a review paper in Nature Reviews of Neuroscience, 100 papers in the literature. That's not complete. Of the traveling waves at every frequency band, every part of the cortex, even in the basal ganglia. The cortex projects to the basal ganglia, and that goes back to the cortex. There are traveling waves in the basal ganglia too. So this is a dynamical system that has many, many parts. So one last piece of evidence here. I wanted to tell you about a project that this is a graduate student of mine, UC Chen, who graduated recently, is now at the actually the University of Washington up in Seattle. And it's a model of the hippocampus. So, the hippocampus gets input from the cortex, and then there's, in the middle of the hippocampus, there's an area CA3, which is a recurrent neural network, a real one. And then there's an output to CA1, and that projects back to the cortex, back to the entorhinal cortex, as you can see here. Now, in addition to this pathway that goes through CA3, there's another one that goes directly from entorhinal cortex to CA1. Now, what's interesting is that there's big time delays here in CA3. So by the time the input goes from EC to CA1 through this intermediate layer, it's going to arrive later in time, and you can compare it to something that happened earlier, and you could use that difference in order to be able to, if the CA3 is predicting the next input, you have that locally available. You have the prediction and the next input available, so you can use that for synaptic plasticity to improve your predictive performance. This is, by the way, the architecture is an autoencoder. Normal autoencoder would simply try to reconstruct the output from the input at the same time, and usually there's no recurrent network. Usually it's one or two more layers of hidden units. But what we're going to do is our loss function is going to be not to reproduce the input, but rather the next input, t+1. And the signals are there in the hippocampus, and this has been known for a long time. So you'll see used back across your time, just the way that everyone uses. And it worked. I'm going to show you examples, and it worked extremely well. But here's the matrices. You actually learn two different environments, and the environment is a rat going through a maze, and then has place fields that are different in each maze. Place fields means that when the rat is at a location in the maze, there's a neuron that fires at that location, and different neurons at different locations, right? And what you can see here is that it learned a Toeplitz matrix. There's excitatory connections along the diagonal and the band of inhibitory connections. And now here's the cross sections here. Both environments have the same cross sections, but this is actually, these are very sparse. If it was dense, there'd be no whites. So these are sparse connections, and they're separate so that they don't interfere with each other. And this is a very small network, 200 units. And so in the hippocampus, you could probably store hundreds, maybe thousands in the same Toeplitz format of the different tasks. Okay, so here's a task. This is a very simple one. You have an input coming from an MNIST handwritten digit data set. And here's one of the inputs, 0 through 9. So there's 10 inputs. It's given them sequentially, and it's got to memorize them. Here's another, it's a different, from a different person, so the numbers are written in a different way. But what you do is you train on many different inputs. And now, after training, you can actually reproduce the sequence, but now it's some kind of average across all of the different digits, as you can see here. In fact, what you could do is you give it the actual input up to 3, and then now you stop, and it will complete it. So this is pattern completion. And now Okay, people say that, oh, these networks, neural networks, they're black boxes. You can't possibly understand them. Well, I can show you. You can actually look at the connections. What about looking at the activity levels? Well, we use independent component analysis. This is an algorithm that was built in my lab back in the 90s to analyze the activity pattern in the network. And it turns out each digit occupies a different part of independent component space. These are color coded, and these are just taken two at a time. And you can see that the whole structure, it learned to put different digits in different parts of the space of activity. So this is good news. It means that we can interpret these networks. But what else can it do? So here, what about movies? So these are sprites, and there's 10 of them, there's 9 of them, and each one has a different figurine with different clothes doing different things. Here it's walking, here it's putting its hands out, here it's putting it's at an angle, you know, one hand waving. So there are different sprites, and we have a bunch of frames for each one of them. And we're going to train this network to reproduce all of these sprites. And it did. It was able, you give it the first frame, and it will reproduce the exact sequence of frames very accurately. And if you now, this is again independent component space. Each one of these is a different sprite, and these are actions now that we're categorizing, not just images. And you can see it does a beautiful job of separating them. One of the important things that the brain has to do is invariances, right? Rotation invariance, translation invariance. So let's, instead of training it on a bunch of digits, let's train it on one digit that is rotated, like 0 and 1. So we trained it on these 2 digits. And then once you give it an input, it then will reproduce that sequence, right? So we can learn these sequences like we price it. But now, when we go into the hidden units and look at the activity patterns using PCA in this case, what's interesting is that each digit that you train on corresponds, activity is actually circulating in a circle, recapitulating the actual movement, the rotation pattern, and each digit is in a different part of the space, separate from each other. So this is, you know, looking into the black box can be very instructive. And so now we have the ability to actually create with predictive coding. This is, by the way, a very, very common thing, because after you know, transformers in GPT are trained to, what's the next word? What's the next word? Well, in this case, it's what's the next action? What's the next action? And the networks are really good at picking that up. So that may be a general principle that we can gather from both the brain and from these artificial networks. Now let's go back to self-attention. So self-attention, here I already told you this is a matrix. So the question is, you know, if we have traveling waves in the brain, how would you implement self-attention, right? That means you have to put things together that are distant in different points in time, coming in sequentially, right? That's what you've got to do. And it may be at different levels in the cortex, and that has to be very, very flexible. You have to be able to learn them. By the way, the self-attention matrix is learned along with the feed-forward weights. So this is something that, you know, Backprop is very good at. So first I want to show you this a very simple correspondence here. Remember I told you that in the transformer, this is stacked. This is just one of the modules in the stack, but you can have these stacked units that then produce an output. Actually, it produces output probabilities, and you can pick, you know, maximum likelihood, or you can put a little noise in and get something a little bit different, makes it more interesting. But in any case, that goes back to the long input vector. There's a sequence that goes back, and as you can see, one word after the next in sequence. Turns out, if you look at the visual cortex, or in fact, the entire cortex projects to the basal ganglia. This is just the motor cortex, different parts of the body projecting topographically to different parts of the basal ganglia down here. And then it returns back to the thalamus to the cortex. There's a loop that takes about 100 milliseconds, right? And so, have you ever thought about where the next word comes from when you're giving a talk? Don't, because then you'll be screwed. Because you'll start standing. But the beauty is that the basal ganglia learns. It learns sequences. It learns sequences of actions. And once you get this going, right, it's just like a transformer. One word after the next comes out. And not just words, actions. You know, playing tennis. And not just playing tennis, but thoughts. Prefrontal cortex also projects that. So you could, without moving a muscle, you could start thinking in sequences of thoughts, right? So it's all the same architecture. It's beautiful. Basal ganglia may be part of the self-attention mechanism. So I have a paper that was just accepted in Friends in Neuroscience, and this was written specifically for neuroscientists to convince them that the idea of traveling waves is a good one, and we have predictions. But one of the ideas that we had, and this is even more speculative, is that, you know, the cortex has this hierarchy I've told you about, and each one has input from the thalamus coming in parallel. But they also project to the basal ganglia. There's an input here, and then there's an output. There are traveling waves in both. But the difference is that the basal ganglia here collects information not just from one area, like B1, but from a whole raft of areas that are related to each other, and then projects back to the cortex. So it's in a position to take advantage of connecting different parts of information in different parts of the cortex and learning their relationship, right? And that's exactly what a transformer does with this big matrix. It could be done, you know, using mechanisms that are known to occur in the basal ganglia. And the dopamine neurons were mentioned. Remember the dopamine neurons? So this is actually one of the most, I think, important discoveries that was made in systems neuroscience in the 20th century, was the fact that reinforcement learning, which goes way back to the psychologists studying, you know, conditioning, back, you know, early days, B.F. Skinner. And people knew that the dopamine neurons had something to do with reward, but they couldn't figure it out because it would, after the first hit, it would decrease, the dopamine response would decrease and disappear. So it's not the reward itself. So what is it? So Reed Montague and Peter Dayan, who were postdocs in my lab in the 90s, wrote a paper saying there's a algorithm in control theory called temporal difference learning, Rich Sutton and Andy Barton. And what's beautiful about it is that you need a signal, which is the reward prediction error. You compare the reward you expect with the reward you get, and the difference you use to learn to predict better in the future. This is a theme. I talked to you about predicting the next step, right? I mean, this is what was used for AlphaGo, right? This algorithm. This is the exact algorithm that was pasted on top of the deep learning cortical network. Okay. It projects very broadly both to the basal ganglia and to the cortex, especially the prefrontal cortex. It took us 2 years to publish this paper in Journal of Neuroscience. The reviewers hated it. I don't know why. We actually did some human experiments and had some predictions and so forth. But it wasn't until it was actually tested in the monkey by Wolfram Schultz. And what was the smoking gun? Smoking gun is you train the animal to expect a reward. The dopamine neuron stops firing. Then what you do is you withdraw the reward. So the monkey is expecting a reward, doesn't get it. Dopamine firing goes down. And the reason it goes down, it was comparing two things. And when there's zero, there's no learning. But if it's not there, you have to learn, oh, it's not there, therefore I should downregulate my prediction for the next time, right? So, and this is now accepted, it's been replicated in humans, and it's an example of an algorithm that came from engineering that actually may be used by biology. And it's more complicated. It turns out that these neurons carry more than just a reward signal. It also carries a lot of information about sensory motor information. So it's richer. You know, nature is much more, takes advantage of these signals for many other purposes. So I'm going to end by giving you a bit of history. So, you know, things are just exploding right now. And it's really exciting to see, but, you know, you read every day about all the faults that, you know, ChatGPT has. It hallucinates, it's unfair, it's biased, it can be offensive, you know. these are real faults, and engineers are working on, guardrails to reduce unfortunately, as you put in fine tuning and guardrails, you actually dumb down the network. There's some people who prefer the full-blown network, and I don't care about the unfairness. I just want to get it's the highest performance. That's something that has to be fixed. Okay, so this, as we may recognize, is Notre Dame Cathedral. It was started in 1066. And it took 200 years to complete. Just think about how many generations worked on this cathedral. Now, why did it take 200 years? Well, the reason is, as they were building it, they didn't have a theory for mechanical engineering. They didn't have Newton's laws. They had very little to go on except practice, trial and error. And so one after another, as they built the walls and the arches, it would fall down. And so they would come up with some bright idea, like if you can see these flying buttresses here. You know what a flying buttress is? It's like a wing that comes out. That's there to prop up the walls. And there's a lot of other things in the arches. If you look at the arches, people say, "Oh, beautiful arches." No, they were put in to keep the ceiling up, right? It took 200 years to figure all that out by trial and error. Well, we're undergoing the same thing. Almost all the work that's been done so far is empirical on these large language models. It's empirical. We're just discovering by trial and error what works and what doesn't work. And there will be a theory that will emerge. Mathematicians can help us, but I think it's actually the physicists who actually come up with the good theories. And my last example is the Industrial Revolution. Remember 250 years ago when Watt created the steam engine? They don't tell you that it would blow up periodically. They didn't have a way to govern the temperature, to regulate the temperature, right? It took inventions to come up with a regulator that was fast enough and was able to keep the temperature from fluctuating and so forth. I mean, that's an engineering problem, right? But they didn't know anything about thermodynamics. That physicists came later and said, "Hey, we can actually predict the temperature and the pressure and the volume, and there's an optimal cycle, the Carnot cycle. We can get much more efficient." And over 100 years, the little steam engine that blew up became powerful, super powerful, and can take millions of pounds and trains across the United States. I mean, this is what happened 250 years ago. Farmers now, you don't need so many farmers. It used to be 98% of us were farmers. Now only 2% in the US, right? And so what happens to the children of the farmers? They go into the cities. And they work in the factories, powered by steam engines. So what's happening now is another revolution. It's not a revolution that's increasing our power, physical power. It's increasing our cognitive power. And that's what my book, The Deep Learning Revolution, is trying to tell us, is that this is something that is going to make everybody smarter. You're not going to lose your job. Your job's going to change, because you're going to be using AI tools. Now, here's what I'm hoping will happen. Perhaps 5 years from now, I will open the New York Times and I will read the front page that neuromorphic engineering has solved the problem with energy, because it's predicted that in 2030, that AI, if it keeps going up in terms of the amount of power needed, will reach like 10% of all the power that's being generated in the United States. That's not sustainable. But the front page will have a headline saying, "Neuromorphic engineering saves the day." And when I wake up, I'll realize that I went to sleep organizing the premier AI meeting to organizing the premier neuromorphic engineering meeting. And with that, thank you.